Okay. So should we get started? All right, so today we're going to talk about triple integrals. And well, we're going to do sort of the first two lectures in one, because we've already had some experience with double integrals of this chapter. But I want to mention what we're doing here. So if we're talking about double integrals, there's an easy thing to say about integration that well, mimics that of one variable calculus. So one variable calculus, you learned that the integral of a function is the area under the curve of the graph of the function, or between that and the x-axis. And we can say the same thing for double integrals. Of course, once we get to triple integrals, talking about four-dimensional volume may be a little disconcerting for some, but there's still a nice interpretation, and it's an interpretation we could have in lower dimensions as well, which is that integrals, say, of density functions, and I'll just use mass as a good example, but you can do other types of density functions, will give, actually probably even better than mass would be something like charge. But mass density functions give, say, total mass within a region. So they give a way of summing things up where those things don't have, sort of constant value, but kind of can change over the region. And the reason I say charge might even be better is because charge can take on negative and positive values. And so there's a notion of a signed type of density, or well, signed charge. So that's a good example to have in mind when you do triple integrals, rather than saying, oh, I'm computing the volume under a graph. You can say, well, I'm computing a total amount of something. All right, but let's get on with it and give the actual definition. So what we want to start out with, so we start with integrating over a box. And I'll call the box B. And what is B? Okay, well, we had a rectangle, AB cross CD, and now we just need to cross this one more time with an interval, which I guess I'll use E and F. Hopefully it won't get confused with functions F or Euler's number E. Okay, so what do I need to do? So I've got a box. And the side lengths here are AB. Well, I guess to be honest, if I'm going to put it in the usual coordinates, I should have AB going this way, CG will go this way, and then EF go up. All right. So let's see here. So what do we need to do to produce an integral? So we'll have a function on this box. So we'll assume, and I'll call the function g just so that I already have an f in here. So assume g is a function with domain containing the box. So just a function on the box B. Then what I need to do if I'm going to actually talk about a triple integral is I need to do all of the things that we don't want to do, but is necessary. So we need to partition. So to get the triple integral, we start with partition. We need to partition now, instead of just partitioning the interval A and B and C and D, we're going to partition everything. So we'll partition AB, X, let's see, what do I want to use here? Let's say L here. Oops, this should be equal to B. This should be equal. I'll partition this interval. This is to Y sub M. It should start, of course, at C and end at D. And then I'll partition this last interval EF up to N. So I'm kind of thinking of this in terms of this sort of cheese grater, where now I slice this up into a whole bunch of little tiny sub boxes. And I can then define, I need to choose, what else do we need to choose? We need to choose sample points in each sub box, xi star, yj star, zk star, and this should be in this sub box bijk, which is going to be equal to this tiny little, sub box. I'll just take each of these tiny little guys and take their product, their Cartesian product. Okay, so I chose the sample points, I've chosen a partition, and I can then make the Riemann sum from all of this data, which gives me an approximation to the total mass if G is thought of as my mass density function. This is just going to be the big nightmare, I equaling 1 to L, J equaling 1 to N, K equaling 1 to N. I put in each of my sample points into here, into G. That gives me sort of a random choice of density inside of this tiny box. And then I multiply by the volume of that tiny box. So this is going to be delta X, I delta Yj. That's the volume, base times width times height, length times width times height, however you want to write it. And there's my Riemann sum. Okay, so what is the integral? The triple integral is going to be, by definition, over our big box B, G, X, Y, Z, dV, V standing for volume, is going to equal the limit over all of our partitions, where we take this norm of the partition, which is the volume of the smallest box in our partition, and we take that let that tend to 0. And we'll say this is what we get for our triple integral, if it exists. Okay, good. This is the definition. This is what it is. But Fubini was not two-dimensional. Fubini was a three-dimensional being, Italian. And he didn't care about 2 dimensions. He was able to say this, that he had a theorem for all dimensions, including 3. And so if we want to calculate this abstractly defined thing, we can write it as, this is Fubini. We can indeed take this as an iterated integral of G. And if I wrote dx, dy, dz, then I would have to first integrate from A to B, then C to D, and then E to F. And now I'll ask you guys, Fubini in two variables, if you'll recall, we had two equations depending on the order of integration. How many do we have here? How many possibilities? Huh? 9? 6? 9 and 6 are my two candidates. Nobody's got 27 or something. 6 possibilities. 6 others. Well, I guess 5 others. 5 more. I'm not going to write them all out. This takes too long. Right? This is the number of permutations that we have with 3. I mean, we've got 3 possible variables, so we can permute these. Think of all the possible ways of ordering X, Y, and Z. We'll get a theorem for each one. There's 6 of those, 3 factorial. Of course, Fubini's theorem in n dimensions gives you n factorial. Then a lot of different options. Nice thing to be able to do. Okay. So what we want to do is we want to jump onto Fubini's bandwagon and see if we can't solve a problem. Doing a triple integral. All right, so let's say we have the following box. -1 to 1, 0 to 2, -2 to 0. So we want to calculate following triple integral. People know what the integral is, by the way? I mean, what this square comes from? I'm sure a lot of you know this. What is that from? What is it? I mean, it's the integral sign for the integral, but what is it? Where does the symbol come from? Nobody knows? Huh? Huh? No? You guys know about like the big like Europe, like continental in English, like big problems back in the day, like before Brexit, 300 years before Brexit. Well, the English have always been kind of a problem for Europe, and I guess vice versa. But anyway. Okay, so well, there was Newton's calculus, and there was Leibniz and all that. And so, but this comes from the German letter S for sun. So it was not Newton's notation. Anyway, I'm just saying, so this is, we're going to sum up this function over this region. Think of this, the sum of all the contributions. Okay. So let's see. What do we want to do? We want to use Fubini. And again, just like in the 2-variable problem that we had, order of integration, you really want to be wise with which order of integration you choose when you're confronted with a problem like this, because some of the integrals are going to be a lot harder if you choose just a random one. So let's see. So I'll rewrite this, and I'll write down Fubini, x, either x, y, z, b. I'm going to write down 3 integrals, iterated integral, write down my function, and then I'm going to see what people think. So I need an order of integration here. So what looks like it's going to be easiest to integrate first? Z. Right. So let's try to see. So let's see if we can explain why. okay? So right here, we see in front of z, we see this xy, and I see a y squared x here, but I definitely see an xy up front. So if I want to like use a substitution here, rather than doing some integration by parts, z certainly seems like it's got enough flexibility. After I did that, I should think, well, I've gotten rid of an xy here, and so I'll just have a single y left. So what do you think the next order, or the next integral should be? X, good. And then y, and let's see if it works out for us. So before we do that, of course, let's make sure we put in the correct endpoints of integration. So we're going to go from -2 to 0. X is going to be -1 to 1, and y is going to be 0 to 2. So I'm just matching up these guys like that. All right. So we go ahead and compute. Leave these first two integrals alone. Let's focus on the one we're going to integrate first. And of course here, we'll see that we'll get a y e to the x, y, z. And we want to evaluate from z equals -2, 0, dx, dy. So we have to go ahead and do that, calculate a little bit. So at z equaling 0, we'll get y times 1. And then at z equaling 2, we'll get y times e to the -2xy. Okay. So I integrate that. I'm taking antiderivatives here. So I have, okay, so what should I write here? People can tell me. Here I know what x is going to be going from -1 to 1. So what about the first term here? What's the antiderivative that I should write? I'm sorry? xy, good, xy. I mean, I think on the, what I'm going to worry a little bit about with the next exam is that people would put some like, y squared over 2 or something. I mean, make sure that you are paying attention to what you're integrating with respect to, is I guess what I would say. And then, okay, so I want to say minus here, but I can indeed write a plus. And because I've got this, and then I'm going to need a 1/2 e to the -2xy. And here I'm just using a kind of a basic substitution. I know that this -2y is going to come out front. I've got a -y, so I need a 1/2. All right, so let's evaluate that. 0 to 2. Here I'm taking, and again, this is just doing it right now. I'm prone to make mistakes here if I don't write this x here. Okay, so when you have many, many variables floating around, it's good to remember what you're evaluating with respect to by just writing it down. So, okay, well, I'll start at the 1. So at x equaling 1, I get y plus 1/2 e to the -2y. And then at x equaling -1, I get -y plus 1/2 e to the 2x. Oh, 2y, pardon me. 2y. dy. Question? Comment? Yeah. Here, this guy. So I saw that I'm integrating with respect to z here. So the term in front of the z is xy. And so here I'm getting rid of an xy to go here. That's why I just have a y left instead of a y squared. In other words, if I took the derivative of this with respect to z, I would get an xy term coming down, and I would get e to the xyz, which is precisely that. So I have to divide by the whole term in front of the z. Other questions? feel free to ask questions. I know a lot of this kind of be unfamiliar, and I know that I'm prone to make mistakes when I'm doing this, so please do let me know. Okay, so we get this expression. Oh, so we have a little bit of a cinch kind of thing here, but that's all right. I'll just write it out. And here, this is it's not a hard integral here. Now we just have y squared over 2. Oh, sorry, no 2, y squared. Y squared. I guess I need a minus 1/4 e to the negative 2. What? How did that happen? E to the negative 2y minus 1/4 e to the 2y. And here I'm going from 0 to 2. Here I'm not so worried about writing down the variables since I don't have any other variables to evaluate. Okay, and so let's finish. We have 4 minus 1/4 e to the minus 8 minus 1/4 e to the 8 minus quantity. Okay, so I get 0 minus a half. So this is going to be so 4.5. Okay, I'll just leave it here. I feel bad now. I should probably, so I don't want to leave these things here because I want you guys to actually write these all the way out on the test. So let me not be a bad role model here. Is that better? Why do I have 8 here instead of 4? People should tell me. 4. Okay, so tell me if have I made other mistakes? Is it clear? Any other mistake? Anything else? Okay, I think it probably is okay. Okay. Okay, good. All right, so this is how you do this. I mean, the computational part, again, don't worry too much if you have little computational errors. The key thing and the most important step and the most important lesson, so certainly there's some technical thing about making these iterated integrals correctly, doing them correctly. That I think is important, but the real difficult part of this problem is choosing the order here. That's the thing that's the most challenging thing for a problem like this. So be cautious at first with your work. Try to be cautious, and if you run into trouble, like if you've done, let's say you've got a triple integral on an exam, and you're halfway through your page and it's looking grim, it's okay to say, all right, I should try something different. Usually that means that that's not the way I want you to try to solve it. I very consciously set these up so that they're not computationally hard. Right? So if they are, then there's probably something wrong with the approach. Okay. So as I said, we're going to do sort of sections 1 and 2 just today for 3 dimensions. And then if we have time, a little more of the next section, which is a little more involved and we're going to need some more time on it. And so what about more general regions? So we don't, just like in 2 dimensions, we don't want to integrate just over a rectangle. 3 dimensions, most shapes don't come in as a box. Like most shapes are more interesting. We'd like to be able to integrate over more general regions. The way that you do that is the same kind of, you take the same approach as you did in 2 dimensions. So if you have a more general region, some blob, inside of your space, inside of 3-dimensional space, say this blob is called E. Well, what you can do with your blob is you can, put it inside of a box. Right? So now you've got a blob in a box. And if you are interested in your function G, that's just defined on on E, so let's say you have a function, a density function on E, you can extend that function so that it's a function on all of this box. So let's call this box B. And so extend this. And the way you extend it is you just let it be 0 outside of your region you're interested in. So in other words, G tilde of XYZ equals one of two things. It either equals G of XYZ if XYZ is in the box, or sorry, is that if XYZ is in the region E, or it equals 0. So this is a function that's discontinuous generally, but it's only discontinuous on the boundary of your region E. And just like in two variables, where if you have discontinuities along a curve, you still are integrable if you're continuous everywhere else. The same is true in 3 dimensions. If you're just discontinuous on a surface in 3 dimensions, and that's a reasonable surface, then you're still integrable. So then you can apply Fubini to this function, and then we define this triple integral over the region E of G. We define it to equal the triple integral over the box of G tilde. That's the definition. So it's all very familiar. And once you have this definition in hand, you can start talking about type 1, type 2, and as you'll have guessed, there should be a type 3 region as well, right? And maybe even more regions. So there's a lot of different ways you can kind of typecast these regions, but the most general kind of approach is maybe, or maybe not the most general, most concrete approach is just to kind of consider a type 1 region. So I'm not going to go through every single type. And if I give you a question on the exam over general regions in 3 dimensions, unless it's using a change of coordinates, it'll be sort of something like this. So let me give you a practical example. You can always change coordinates to kind of be in this example. That's false. Okay. Many times you can change coordinates to be in this example. So let's let D be a region in the plane. And let's take 2 functions. And it'll be like the functions we had over 2 variables. We're gonna have some bounding functions, U1, U2, 2 continuous functions. And defined on D. Then we can talk about this region, sort of like our type 1 region here. So let's consider the region E in 3 dimensions, which satisfies, it's all XYZ satisfying well, XY is going to be in my domain D in the plane. Oops. And Z is bound by these 2 functions. So if I put, it's basically Z is trapped. So we're looking at the region between the graphs of these 2 functions over the region D. So let me draw that picture here. So let's say we have this, region here. This is our region D. Over D, we have these kinds of these functions. So this is like the graph of some function. This is Z equals U2 XY. And then we have some other graph maybe it's, I'll just draw it this way, is z equaling u1 of xy. And so what's our region E? Well, we look at all things sort of, well, let me make my graph a little larger, all things that are sort of stuck in between these. This is E. So it's the blob of things sort of stuck between the two graphs. Three-dimensional region. Sorry, the sketch is kind of sloppy, but okay. Hopefully it's understandable. So then for these types of regions, we can actually do computations as the point. Before we define the triple integral, but now we have a way, Fubini tells us a way of calculating it. Namely that if I take this triple integral over E of, here I'll use the function f, say I have x, dv. Well, now what you do is not write it as a triple integral, but rather write it as an iterated integral where one of the integrals is a double integral, the other is a single variable integral. So what you're going to do is you're going to first integrate out the z variable. So this is going to go from u1 of xyz of xy to u2 of xy of f of xyz dz. You're going to take that guy, do that. Now you have a function of two variables, and now you take the double integral over the region D of that guy. So it sort of leaves options open for you as far as what order you would like to integrate x and y, or if you would like to use an alternative coordinate system. So this is the main kind of non-box region that you might want to know how to handle. All right, so let's do an actual problem that looks at such a thing. And I'll write a region that we've actually seen before, but we'll do some, I think before we did the volume of this region, now we'll actually do a triple integral of a function on this region. All right, so let's let E be this region. It's going to be the set of points x, y, z, and they'll satisfy this inequality, x squared plus y squared less than or equal to z. Maybe I didn't do this one last time. I think I did a z squared last time. Did the cone or something. So this time it's slightly different. Same, close to the same idea. So let's calculate following triple integral. Take the triple integral over E of z, just a simple function. As you get more variables involved, even simple functions can present complicated, well, they become more complicated. So this is a triple integral of just the function z, of height, essentially. Again, what I said, I don't know about last lecture before, still applies. It's really, I find it helpful to sort of get a picture of what you're integrating over before you start chugging along. And so for that, again, we can look at where these bounds are actually attained. Maybe the simple one to start with is where this bound is attained. It's where height is equal to 1. So if I'm going to draw sort of the graph of this region, I know precisely what that bound is. That bound is just, you know, we get a z equaling 1. So I know that since z is less than or equal to 1, my whole region has to be, you know, below this plane that's up at height 1. Now, what about this bound? Well, that bound is a paraboloid. It's just sort of our standard paraboloid, which I'll just sketch by hand. So if z is less than 1, but z is greater than the graph of this paraboloid, then we're stuck sort of in this region. This is our region E. Now, the question is this a region that looks like this region up here? And the answer is yes. We've got z trapped between two functions. First function, the u2 is the constant function 1, and the u1 is this function x squared plus y squared. Now, that said, what is our region D on the plane? Well, for that, we can just project down. If we project down, we can see that this is going to be a unit disk. Or you can solve the equation when both of these are attained. So if we have equality, we get this equation. So this boundary up here is satisfied right when x squared plus y squared equals 1. So it's a unit circle. And of course, everything inside of that unit circle is going to be our unit disk. So here, our D is the unit disk. So now, with everything in mind, we have our two functions, right? So let me just write that down. We have our two functions. This is u2. This is u1. And we have our disk, so we can write this formula and try to evaluate this triple integral. Try to move this over so I can keep that formula there. So we've got this function z dv, and I'm going to write it as a double integral over our unit disk of this integral with respect to z. And here our lower bound is x squared plus y squared. Our upper bound is 1. We're going z dz dA. Now I can just go ahead and plug away. I get the double integral of z squared over 2, 1 x squared plus y squared. Here, if you want, you can let, maybe it's good to say this thing. Sorry, let me write z. Okay. Okay, this isn't too bad. Double integral over d. 1/2 minus x squared plus y squared squared over 2 dA. Or if you want, I'll pull the 1/2 out just to simplify the look of this 1 minus. Okay, so now do I have a type 2 or a type 1 region for my domain D? Someone said both are right. Should I use type 1, type 2? Should I do something completely different? Any suggestions? Type 1? Nobody wants to go out on a limb? What do you guys think? Who? Oh, polar. Thank you for going out on a limb. Saved us all a lot of time. Yeah. I'm integrating over the unit disk. I see x squared plus y squared in my integrand. That should, like, the alarm bell should go off when you're seeing integrals like this. Maybe the most instinctual thing is to go into type 1 or type 2, but fight your instincts. Control your instincts. I don't know. Do whatever it takes. Let's go over let's use polar coordinates, because polar coordinates make this integral much, much easier. So here, the unit disk can be described as theta between 0 and 2 pi, and radius between 0 and 1. And as I said, x squared plus y squared, that's r squared, And I'm squaring it, so I get r to the fourth. And I want to write dr d theta. Is that okay? Wait, why, what's all this murmuring? What's all the murmuring? There needs to be an r, right? I made a mistake because I'm prone to doing it. All right? Please, please don't make these mistakes. Don't be like me. Be better than me. Like what I tell my kids. Okay. You get this, now we can integrate. Now life is really easy, right? We know how to integrate polynomials, and we've got a polynomial in R. So we've got R integral is R squared over 2, R to the 5th integral is R to the 6th over 6. And we're evaluating from R equaling 0 to 1, d theta. So a half minus a sixth is a third. So I can bring that a third out, and I'll get 1/6 integral from 0 to 2 pi d theta, which is, okay, 2 pi, so that's pi over 3. Now that was very quick. I hope you'll see a lot quicker than trying to, go from upper bound square root of 1 minus x squared or something like that. You don't want to do that. Okay, so this is basically it. This is it for triple integrals, and we will see that there in a next lecture we'll start to see that we can do integrals using other coordinate systems, and maybe do some fancier triple integrals than we did today. But this is it for rectangular boxes. I want to end though today's lecture kind of getting ready for next Tuesday, where we talk about change of variables. And I'm not going to do triple integrals or double integrals or anything like that, but I did want to discuss, there's a notion of change of variables just in one variable, and what it is and its relationship to a more simple notion of just u substitution. Okay, so I want to look at, and the reason I want to cover this is because there's a way of looking at change of variables that's the right way, and it's sort of to some degree opposite of the way you do change of variables in one variable, in some sense. Okay, so I want to look at a simple integral, very simple integral. The integral, let's say of 2x e to the x dx. I'm going to integrate this. I think people can get behind this integral. All right. Oh, let's say I'm going to do like 1 to 2 or something. This is an integral. So the way I think about this is I've got a function on x, and I've got an interval on the x-axis, on the x line, 1 to 2. And I'm considering this function as maybe like a density again, some kind of mass density on this interval 1 to 2. Now we all know how to integrate this, right? What do we do? What do we do? What do we do? X squared. Sorry. What do we do to integrate this? Thank you. Well, I mean, we know how to integrate the other one too, but this one's more of what it's a very simple integral. Thank you. What do we do now that I've written it correctly? U substitution. U substitution. We say, okay, let's let u equal x squared, right? And let's let du equal 2x dx. Well, we don't let it. This is what it happens. And then we say, okay, this integral is the same as this integral of e to the u du, right? And now what do I have to do for my bounds? What are my bounds? So what do I get? 1 to 4, right? Now, this is a computational tool, and you can see it as a computational tool. And in one variable, it's actually more flexible than ever, but it's a very nice computational tool. But I wanted you to think about it in a different way in preparation for next week, or And that is, we also have this other line, this u line. And we have this interval 1 through 4. And we have this function. So here we have this function, which is okay, so e to the x squared, let's say. And here we have this function e to the u. And what I want you to think of is I want you to think of this as being, so we have this function here, which sends x to u. So this is u equals g of x. And the question is, if to sort of reverse this process. So when you look at this, you do use substitution to simplify it into an integral like this. But what I'm going to ask you to do is to think about it in the opposite way, which is suppose we have an integral like this on the u line, a very simple integral, but now we change our variable from u to x. So now instead of thinking of this integral just being on the line u, we have a function where we write u as a function of x. And this reparameterizes our interval. And we want to stick this function in to our guy. And what we would like to do is we'd like to say, okay, well, the integral here is equal to the integral we had 1 to 2 of e of g of x. But we can't then write dx because when we did this function and changed parameters, we also changed the length, right, of these little subintervals so that they got longer. And the estimates of that change are embodied here. They're in the derivative of g. So we can't write g of x, we have to write g prime of x. So this is a change in length that we're bringing into this change of variables. Now what we're going to see next time is we have the same kind of process, but now, again, we're going to start in this world. You're going to have a region, most commonly a complicated region. And you're going to want to integrate over it. And what you want to do is you want to, so maybe you have some variables u and v here. You want to say, well, I have a way of mapping a rectangle into this region. And I want to change my variables from the uv variables to my xy variable set. So what do we have to do to the dA in that case? How can we adjust our differential in that case? And that's what we're going to talk about next time, but I'll let out a little early this time. Okay?